All right, welcome to the Explainer. Today we're doing something a little different. We're going to look at the weather from a pilot's point of view. We're talking about those invisible forces that make every single flight a safe one.
I mean, look at that. The sky is gorgeous, right? But for a pilot, it's also this incredibly complex environment that they have to understand. So how do they do it? Well, let's dive in and see how pilots actually learn to read the language of the sky.
Okay, so first things first. Before any flight, a pilot has to think about what they're actually flying through. It's so easy to forget, but we're all living at the bottom of this huge ocean of air. And for a pilot, understanding what's in that ocean, well, that's step one for any safe trip.
So you might think air is just, air. And for the most part, its mix is super consistent. We're talking 78% nitrogen, 21% oxygen. But here's the kicker. The real game changer for pilots is this tiny little variable component, water vapor. That's the secret ingredient, the thing that creates all the weather, from a little puffy cloud to a massive thunderstorm.
And pretty much all of that weather, it happens right here, in the lowest layer, the troposphere. This is the pilot's playground. And in this layer, you've got these three invisible forces, pressure, density, and temperature, that are always at work, shaping literally every part of a flight.
Okay, so we've got these invisible forces messing with everything. Pressure, temperature, density, they're defining the skies. So how on earth does a pilot in Japan talk about this stuff with a pilot in Brazil and have it mean the same thing? How do you standardize it? Well, the answer is pretty clever. They came up with a universal baseline that the entire world of aviation agrees on.
They call it the International Standard Atmosphere, or ISA for short. Just picture a perfectly average, totally theoretical day. Now, let's be clear, this perfect day pretty much never happens in real life. But that's not the point. The point is, it gives everyone a common starting line. It's like a universal yardstick. Everything that's actually happening out there is measured against this standard. It makes sure every pilot everywhere is speaking the exact same language.
So on this perfect ISA day, at sea level, the temperature is a nice plus 15 degrees Celsius. The pressure is 1,013.25 hectopascals. Don't worry, that's just the unit they use. And as you go up, the temperature is supposed to drop by about 2 degrees for every 1,000 feet you climb. So that's the ideal, right? The baseline. But here's the thing. The real world almost never follows these rules exactly. And it's in those little differences, those deviations, that we find all the weather. So how do these tiny little deviations from that perfect day, how do they create something as simple as a breeze or as powerful as a hurricane? It's amazing, really. It all boils down to one thing, how different temperatures create massive systems of pressure.
The best way to think about it is like the atmosphere has its own terrain, its own landscape. High-pressure systems, they're like giant invisible mountains of heavy sinking air. And low-pressure systems are like deep valleys of lighter rising air. And what happens when you have a mountain next to a valley? Stuff flows downhill. Air is no different. It's always trying to flow from those high-pressure mountains into the low-pressure valleys. And that flow, that's wind. That's what drives all our weather.
So, in the northern hemisphere, it works like this. High-pressure systems spin clockwise, pushing air down and out, and that usually means nice, clear weather. Low-pressure systems do the opposite. They spin counterclockwise, sucking air up, and that often brings clouds and rain. Now, for a pilot, getting a handle on these patterns isn't just interesting. It's absolutely critical, especially for one specific instrument in the cockpit.
And that brings us right to the cockpit. We're talking about the altimeter. At its heart, it's just a really sensitive barometer that's been relabeled to show altitude instead of pressure. But for a pilot, setting this thing correctly, it's not just some box to tick on a checklist. It is, and I'm not exaggerating, a matter of life and death.
Okay, so pilots are constantly adjusting this. Near the ground, for takeoff and landing, they set their altimeter to the local pressure, which is called the QNH. That tells them exactly how high they are above sea level. But then, once they get up to a certain cruising altitude, every plane in the sky switches to that standard setting we talked about, 1013. Why? So that everyone is on the same page. It makes sure every single aircraft is using the exact same yardstick, which is how you keep them safely separated from each other up there.
This all leads to a simple little rhyme that every pilot has burned into their brain. From high to low, look out below. Think about it. If you fly from an area of high pressure into an area of low pressure and you don't adjust your altimeter, the instrument gets tricked. It thinks you're higher than you actually are, but in reality, Your plane is dangerously, dangerously lower than your instruments are telling you.
And pressure isn't just about telling you how high you are. It's a huge deal for performance too, because the density of the air has a massive effect on how well a plane can actually fly. So let's think about this. What's the absolute worst-case scenario for getting an airplane off the ground?
It's this little trio, hot, high, and humid. That combination creates the thinnest air possible. Thin air means less lift from the wings and less power from the engines. It's bad news all around. To deal with this, pilots use a calculation called density altitude. Basically, it tells them what altitude the airplane thinks it's at. You could be at an airport that's 5,000 feet high, but on a hot day, your plane might perform as if it's at 8,000 feet. That's a huge difference, and you have to account for it.
All right, so we've talked about pressure and density. Let's get back to that idea of air flowing from high to low. Let's talk about how that creates wind, the actual currents of air that pilots have to navigate through.
Okay, this is one of my favorite little rules. It's called Bayes-Ballott's law. It sounds complicated, but it's so simple. In the northern hemisphere, if you stand with the wind hitting your back, the area of low pressure will always be to your left. That's it. It's all because the Earth is spinning, and it lets a pilot build a quick mental map of the whole pressure situation just by feeling which way the wind is blowing.
Way up high, thousands of feet in the air, there's basically no friction from the ground. And up there, the wind is this really cool balancing act. You've got the pressure gradient force trying to push air from high to low, but you've also got the Coriolis force from the Earth's spin that's trying to deflect it. When those two forces are perfectly balanced, you get what's called the geostrophic wind, and it just flows smoothly right along the lines of equal pressure.
But as you get closer to the ground, friction messes everything up. The ground literally drags on the air and slows the wind down. When the wind slows, that Coriolis effect gets weaker, and that perfect balance is gone. So now the wind starts to cut across those pressure lines, heading more directly towards the low pressure. And that is why the wind you feel on the runway is totally different from the wind just a couple thousand feet up.
So let's tie all this together. What does this all mean for the pilot in the cockpit? Well, understanding all of these invisible forces, it's not about acing a test. It is, quite literally, the foundation of flying safely.
Think about it. From the second a pilot starts their pre-flight briefing to the moment the wheels touch down, they are constantly building and rebuilding this mental model of the weather. They start with the baseline, the ISA. Then they look at the big picture, where are the highs and lows. They dial in their instruments to match reality, they predict how their plane's going to perform based on the density, and then they navigate the winds. Every single one of those steps is a critical link in the chain of getting you home safely.
So hey, the next time you're on a plane looking out that little window, I hope you don't just see clouds. I hope you'll be able to picture these invisible forces at work, these mountains and valleys of pressure, the currents of air. You'll be seeing the language of the sky, the same language your pilot is reading constantly to guide your journey safely home. Because for them, meteorology isn't just science, it's what they do to fly safe.